increasing access across apps, addressing color blindness barriers. Speaker, Arvind Sundaram, Senior Principal Engineer, Intel. Moderator, Daryl Adams, Accessible Technology Innovator.
Thank you. And thank you to SiteTech Global for producing this conference and bringing this leading edge technology to the forefront and shining a spotlight on vision tech. I'm Daryl Adams, and I recently left Intel after 28 years, where I was the Director of Accessibility. I'm now pursuing new ways of defining and driving assistive technologies to help people with disabilities live better lives. And I'm currently chairing the Consumer Technology Association's Accessibility and Age Tech Working Group, where we hope to bring the industry closer together and really realize that vision where technology can be of better use to people with disabilities and for the aging population. I have retinitis pigmentosa, so that means I'm losing my eyesight from the outside in. And I think most people who are on this path, who have some experience with progressive sight loss, realize it's a journey, and it's really challenging to continue to have to relearn what you can and cannot do, and how you can and cannot rely on your eyesight. But it's such an incredible time where we're able to also get a glimpse into the future of this fantastic set of technologies that are becoming available. And at this conference today is just is a way to highlight just all of the fantastic capabilities that are becoming available to us. So I'm really excited to be here and also to experience all of the different technologies that will be shared today. Today, we're going to be sharing some of the great work that Intel is doing to improve the digital experience for people who are colorblind. But before we get into that, I want to talk a little bit about the history of Intel and SiteTech innovation. Starting back in around 2007, 2008, Intel created a product called the Intel Reader. This was a handheld device that was specifically developed to and designed to help people who are dyslexic or who are visually impaired or blind be able to interact with written documents. So it basically would allow you to scan the document, and then it would use OCR to read it back to you, or optionally, if you had sight, it could enhance the text so it would be easier to read. Keeping in mind, this was right as the first smartphone came onto the market with the iPhone. And so it was fairly quickly evident that over a number of years, this technology would be something that would be performed in the phone. But when it launched in 2009, it was a really fantastic product that had a lot of utility for the blind and low vision community, as well as the dyslexic community. The thing that was most interesting about this to me was that this product was the brainchild of a single employee at Intel who was dyslexic and had a passion for trying to try to figure out how to solve for his own needs. And he took that vision, made it his mission, and created a product, and it was successful. And so from that point forward, I realized that you can, as an individual, if you have the right drive and passion, you can make things happen, even at the largest companies. The next thing I'd like to bring to your attention is the spatial awareness wearable. This was back in 2014, so 10 years ago, Intel developed a wearable technology based on a RealSense camera, which is a 3D depth sensing camera. And we put it together with a number of haptic actuators that were positioned on a person's body. And it would basically allow someone to move through space and be aware of their surroundings based on haptic feedback. No AI involved, but it was all based on the cutting edge sensing capabilities of the time. And I actually had the opportunity to demonstrate this capability on stage at the keynote, or Intel's keynote, at CES in 2015. More recently, Intel had been partnering with Good Maps to work on improving indoor wayfinding. And in particular, we were interested in making more effective and more accurate and more effective use of LiDAR scanning technologies. So that way, solutions like Good Maps can scale more efficiently and more quickly so that more people can take advantage of the benefits of having really accurate indoor wayfinding maps. So as we move into the future, my vision is that AI is really changing our relationship with technology. We are at a point where the technology is going to be able to improve our communications and ultimately improve human connection and our level of shared understanding. Think about it as the technology is becoming more sophisticated, it's also blending into the background. So we're going to have less computing interfaces and more human interaction. And our devices are also learning how we communicate. So for the first time after decades, instead of people needing to learn how to use technology and how to use and have that learning ramp, that learning curve, technology is beginning to understand us fundamentally and will work with us. So this is going to be a much more natural way of interacting with each other and with technology. In addition, our devices will fundamentally understand our needs and preferences as individuals. And this is, consider the idea that your computer or your device will understand how you hear or how you don't hear, or how you see, or the things that you're unable to see, and will correct for that in real time. So this is where we get into today's topic, where Intel is developing technology to help people who are colorblind be able to get full benefit from what they're seeing on their displays. And this is done by first understanding what somebody can and cannot see, and then applying a filter at the graphics driver level, so that everything that is rendered to a display is able to be seen in a useful way for that individual user. So I'd like to now introduce Arvind Sundaram, who is a senior principal engineer in the client computing group at Intel. Arvind and his team have been working on this technology, and he'll now go through the details for how it works. Arvind, over to you.
Hello, everybody. Thank you, Daryl, for the wonderful introduction, and thank you, SciTech Global, for providing us this wonderful platform and opportunity for us to bring together and showcase this fantastic technology that we are super excited about. So I'm here representing Intel, and my name is Arvind, and I'm a middle-aged male of Asian descent. And I'm very happy and excited to talk about one of the technologies that could really help color-challenged individuals. So we are going to talk about, and I'm going to introduce the tool that we are developing, and also talk about how it is planning or how it is meant to help people with color challenge or color perception challenges, right? With that, so let me start. Okay, so with that background, let me quickly run through as to what we are going to talk about in this presentation. So I will start off with the problem statement. We will quickly look into the problem statement, and we'll also look at what is color blindness or color perception challenge. We'll quickly look at what are the different types, and then I will run into the solution space. We will look at what exactly we're trying to solve, how are we going to solve, and I will walk through a step-by-step process of explaining. I'll also show as to what kind of a test it's going to be doing and what are we deriving, and maybe slightly peek into the algorithm and see what exactly we're trying to derive. And then lastly, I will show as to what the user interface is, and then look at when the whole system or the whole application is going to be available, and what are the next steps, right? Okay, so with that, let me quickly introduce the problem, or bring the problem statement. So color perception is something that is more often taken for granted, but however, reduced color perception is more common than expected. If you go by statistics, it's as much as 8%, and of specifically the male population, they have challenges in perceiving colors. But if you look at contrast deficiency and other defects, it could be as high as 24%. That's almost a mind-boggling. A fourth of the male population have some sort of a visual perception challenge. So we started off and looking at how can we address and how can we help this particular group of individuals who have color perception challenges. So if you look at the current industry, and also a lot of professions are increasingly dependent on slideshows, illustrations, and these use a lot of colors. They use a very wide color spectrum. So we are basically depriving, as much as I could say that we are depriving a significant portion of our population of the ability to perceive or even appreciate all these slideshows and illustrations. So what, I mean, are there no solutions? Yeah, there are some solutions which are out there. The operating system, for example, and there are some specific tools that are there out in the market, which provide for color correction. But we did find out that the process is not very user-friendly, can be quite cumbersome, and you're basically playing with millions of colors. So it's never possible to get the exact color correction per se if you want to look at. So we'll look at what exactly is color correction. So it's not exactly that easy for an end user, and it can be even quite frustrating as well. And also there is an increasing need for a simple, low cost yet effective automated tool that can identify the user's color perception, the deficiency of it, and apply the corrections that at the device level and verify if the correction is indeed effective. So Daryl talked about the PCs being more perceptive, being more user attentive. It perceives what the user can see and not see, or hear and not hear. So this is one step towards making the PC more smarter, bringing intelligence to use, putting it to use, and then identifying what the user can perceive and what the user cannot perceive, and then make appropriate changes so that they can appreciate what exactly is being shown on the display. So that's our attempt. So now with that, let me quickly look at what exactly is color blindness. What are color perception challenges? So we humans perceive colors, especially there are three basic colors, red, green, and blue. And there are certain sensor elements within the eye, which we call as cones, without going into the specifics. So these are this main sensory nerve endings, which are responsible for the user to perceive colors. A significant portion of the population can perceive a wide spectrum of colors. However, there are a certain group of individuals who can or who do have perception challenges. So when I say that a person cannot perceive red, it's not that they cannot, for example, they are called as protanopia. So it's not that they cannot see the red, but it's just that they don't see it with the vibrancy that a person with a normal vision can perceive. So which means they see the other colors basically derived out of green and blue much more pronounced as compared to red. Similarly, if the person has green deficiency, if the person has blue deficiency, so we have different colors and also a combination of these colors, which the end user may not be able to perceive. So as you can see, so a user may not necessarily have only the red deficiency or only the green, but a combination of these as well. So that's where the complication comes when it comes to the application of a correction factor. And that's where we felt the need for an automated tool which can identify these mix of color deficiencies and also look at how much the correction needs to be done, and everything is done in the background. And it's a matter of just a few minutes before the display starts correcting itself. And then the end user gets a display which is perfectly calibrated for their eyes. So that's the goal. And then with that approach, let's look at how do we get the solution? What's the approach that we are taking? So the approach is not very different from what a professional or a doctor would use to basically look at what's the perception or color perception deficiency that the user has. So we drew inspiration from the standard Ishikawa test, which is a test for color blindness. And we have derived charts out of this, which are very similar to what is used by professionals. We use these charts on an online format, so which means the PC or the device or the computer which the end user is using. So we present these as slides. So you'll shortly show I'll shortly show the demo, but you can see that these are charts, which are standard charts, which contain color coded numbers or images of objects or animals. And these are presented to the user, and the user is required to select as to what they see. For example, if the number is shown, so the user is provided a multiple choice, and they pick one of the choice which is representative of what they are seeing. And based on these inputs, so we have about 85 color charts which are presented in succession. And based on these, the inputs, they are a clear idea of the color perception deficiencies identified. It's also recorded. And based on this, the algorithm picks up what correction needs to be done. And we will see as to what and how it's derived. And then based on the correction, the entire display changes much to the benefit of the end user. So now we basically increase the contrast and increase or decrease the contrast of certain colors and spectrum so that it compensates for the lack of perception or lack of color perception capability of the end user. So that's the overall very high level approach. However, let's go step by step, and maybe we can go peek a little bit under the hood and see how it works. So as I mentioned, this is a very standard color perception test. We start off with a standard color palette. I'll show a few color palettes here and also explain as to what is being shown there so that you can get an idea. And it's used by experts, professionals to identify the extent of color perception deficiency. So I'm going to start off an automated test here where you will be seeing a succession of about 20 plus slides, which will show the charts. Right, starting off with this. So what I'm showing here, what you might be able to see is a ball which with multiple small balls of different colors, but hidden within this is a number. And if you have a normal perception, you'll be able to see that it's a number 3, which is hiding here. However, if you have certain color deficiency, you might see a different number. So that's what the application is trying to see and hear from you as to what exactly are you seeing. Are you seeing the number 3, or are you seeing something else? So the multiple choices will basically be looking at what exactly are you seeing. Similarly, if you see this chart, so if you have a normal perception, a normal color perception, then you will see the 42 as a number. However, if you're not able to see this, but if you're seeing only 4, you might, some people might only see 2, some people may not even see any number, they just see a collection of black and white balls. So that's also an option. So that is given. So you will see that deliberately that these charts are positioned at different corners of the display. It's not in one single area, because it's trying to, what we are trying to gauge is, are there color perception challenges and is it changing with the corners, and is it different in the middle? So we are trying to perceive across different corners of the display and try to see as to what is it that you're looking at and what is that you perceive. And based on that, it's trying to gauge what's the depth of the color deficiency, perception deficiency that the user has. So here you see the number 5 being displayed. However, some people may only see a circle with orange and brown dots, right? And similarly, you have here. So I'm going to show as to a sequence of these as to how these numbers look like. And of course, I just use the example of numbers here, but we also have black and white charts. We also use charts with pictures of animals, pictures of objects. So they are deliberately made in such a way that they can invoke any different response. And we are basically looking at what the user is responding or how the user is seeing it as. So in other words, let us, the step two, we go into the step two of it, wherein we look at the algorithm. The algorithm is now looking at what is your response. For example, let me try to explain that with this slide here. On the bottom left, you will see the chart which I had shown earlier. So here you can see that it's an image which has the number 6, but then there are multiple choices. Let's assume that you chose, hey, I don't see anything. So in which case you don't perceive red. So which means there is a line that we call as the confusion line. So the reason why we call it the confusion line is because the user cannot see this line. So we say that, okay, the user is confused and say that, okay, they cannot see the red. So similarly, if it is a G or a green, so then we call it a green line. If it is a blue, it's a blue line. So we derive weightage for all of these colors or these three basic colors. And we try to find out what exactly is the combined number for all these three basic colors. So let's take an example here. If you are able to see nothing in this chart on the left, bottom left, so then we give a weightage for R as 10, which means 10 is the maximum, which means you don't see red at all. If you're able to see 6, then it's a normal vision as compared when you're looking at red as specifically. So then the R is given a weightage of 1. If you see 3, it's a 4. And if it is 8, the R line is 3, but the B line is also 3, which means we're trying to also look at not just the single basic colors, but a combination of these colors. So now we have a succession of these charts, so which are deliberately positioned and also very specifically chosen so that we can look at all the colors that are needed, and then we derive a weightage for each of these, and then based on this we derive what we call as matrix multipliers. So we do a matrix transformation, and our approach is not to enhance the color but rather enhance the other colors. Say for example, if the person has protanopia, which is red deficiency, so then we enhance the green and blue so that you basically look at or de-emphasize it so that you actually look at the entire image in the right intensity as it was intended originally. The same way we are doing this de-emphasis rather than emphasis, because then there is a possibility that the colors might get saturated. We might actually hit the display limit. So we are looking at the inverse application, which is the de-emphasis part. So while we are working on this, we are also taking account of luminance adjustments, because as we talked earlier, not just color deficiency, but a lot of people also have problems perceiving contrast. So we also do luminance adjustments. And here is where we are actually trying to make use of the compute capability that the PC has to apply what is appropriately needed. And then we apply it right at the graphics driver itself. So which means there is now no hardware change needed. It's just a software which uses the input that it collects from the user, makes a few modifications to the way that the colors are displayed on or generated, and then it puts it on the display. And once the correction is applied, we also rerun the test and the efficacy is also checked. So that's something which we are doing. And that leads us to the last step, which is the user interface. So all of this comes, the chart, presenting the chart, the algorithm, and the application to the driver. Everything is packaged in a single Windows application. So the application can be run at will, or it can be run once in 6 months or whenever the user is logging in for the first time. So it's completely up to the user. The results are also stored in the device against the user login. So which means every time the user logs in, automatically the corrections are applied. However, if someone else logs in, the application, the app may not apply the correction. And also there is a built-in periodic retesting so that with age-related degeneration is also accounted for. And again, the user is given the option to go back to standard color table as and when they need it without any challenges or without any issues whatsoever. So that's where we are. So what will the user see post calibration? So here I'm just showing an image. So which is basically, again, taking the example of a person who has red perception challenge or protanopia. So they don't see the red colors popping out. So they see the color display, and this is deliberately flushed so that person with a normal vision sees the way that a person with protanopia will see this. However, with the correction, they will see that the red colors are popping, right? So they can actually appreciate the contrast and the colors that basically exist. So that's our intent. That's how we see it. So in conclusion, so the application software is something that we have already developed, and it can be run on any PC. We are not limiting it to any CPU or GPU combination. It can be across the board, can be used on any CPU and GPU combination. However, we will also be offering this as a standard offering to any PC, any Intel PC buyer. So we are right now at the stage where we are conducting field trials, and we have, at the time of recording, the feedback of various different user trials are already being collected. We are also collecting feedback on efficacy and also user inputs, and it's being implemented. So we at a Team Intel, we are looking at making this application available for general public from the second half of 2025. And we'll also be bundling this as part of Intel's next generation PC offering, which will be Q2 of 2025. That brings me to the end of this presentation. I would really like to thank SciTech Global for providing this wonderful platform and opportunity. And I'm really excited to see this technology coming to the forefront, and I hope it helps people who have visual perception challenges. Thank you.
Thank you, Arvind. This actually, it brings to mind, in my previous role, leading accessibility and also leading the Disability Leadership Council at Intel, many times employees and managers would confide in me that their accessibility challenges in the workplace. And most of the time, these were things that they were not comfortable speaking of publicly or gaining accommodations. It was just something that they would be dealing with. And color blindness was a very common component of this. They would say, "Hey, by the way, I'm colorblind, and I'm always being asked to be reviewing these dashboards with red, yellow, green indicators, and it's so challenging." And it's such a common thing in the business world to do that with red, yellow, and green in particular. And while there are lots of ways and techniques that we can use for accessibility to help people design things more thoughtfully to include everyone, it's solutions like this that are fundamentally designed into our technology, into our computing platforms, that can really just make this universally useful to everyone. So I'm really excited to see how this transpires over the next couple of years. And just to reiterate Arvind's points, that Intel does plan to make this capability broadly available in the second half of 2025 on new PC platforms. And the technology is not proprietary, and so it's not necessarily that you have to buy an Intel system. We want to make sure that it is a technology that everyone can benefit from. And for more details, you can also read the research paper Arvind's team has produced, and that will describe this solution in much more detail. So thank you, everyone, for tuning in today, and thank you again to SciTech Global for really shining spotlights on the latest advancements in vision tech.